Look up at the night sky. What do you see? A blanket of twinkling stars, each a distant sun, scattered across the vast expanse of space. From the heaviest elements to the very planets we inhabit, all owe their existence to the life and death of stars. Stars are dynamic, ever-evolving celestial bodies, each on a unique journey of birth, life, and death. Join us as Edisla embarks on this captivating exploration, delving into the heart of stars to unravel the secrets of their existence and the profound impact they have on the universe. Our journey begins in the cold, dark depths of space within massive clouds of gas and dust known as nebulae. Within these swirling clouds, gravity reigns supreme, pulling together atoms of hydrogen, the most abundant element in the universe. Over eons, these atoms clump together, forming dense pockets of matter. At the heart of these collapsing clouds, a protostar emerges, a hot, dense ball of gas teetering on the brink of stardom. The journey from a nebula to a protostar is a testament to the power of gravity, shaping the universe one star at a time. Imagine a vast ethereal cloud of gas and dust stretching across trillions of miles of interstellar space. The catalyst for star formation often comes from outside the nebula itself. Once this collapse begins, gravity takes center stage, pulling the gas and dust particles closer together. This delicate dance between gravity, density, and temperature sets the stage for the birth of a star. Deep within the collapsing nebula, a dense core begins to form, marking the birth of a protostar. As more material falls onto the protostar, its core temperature and pressure continue to rise. The protostar emits intense radiation, primarily in the infrared part of the spectrum, a testament to the immense heat generated by the infalling material. The protostar continues to accrete material, growing in mass and temperature, inching closer to the moment when it will ignite and take its place among the stars. As material falls towards the protostar, it begins to spiral around, forming an accretion disk. Accretion disks play a crucial role in the formation of planets and other celestial bodies that may eventually orbit the newborn star. Within these disks, dust grains, icy particles, and gas molecules collide and stick together, a process known as accretion. They are the cosmic construction yards where solar systems are assembled, piece by piece, from the remnants of interstellar clouds. Deep within the heart of a collapsing cloud of gas and dust, a protostar continues to gather mass, its core temperature and pressure steadily increasing. Finally, when the core temperature reaches a scorching 10 million degrees Celsius, hydrogen atoms fuse, creating helium. This process, known as nuclear fusion, is the engine that powers stars, releasing an incredible amount of energy. At this moment, the protostar officially becomes a star, embarking on the longest and most stable phase of its life, the main sequence. The main sequence is characterized by a state of hydrostatic equilibrium, a delicate balancing act between gravity and radiation pressure. Gravity constantly tries to pull the star's material inward, while the outward pressure from nuclear fusion counteracts this pull. This balance is dynamic, constantly adjusting to slight fluctuations in the rate of nuclear fusion. This constant interplay ensures the star's stability over billions of years. The main sequence, though a period of relative stability, is not eternal. For stars on the main sequence, this fuel is hydrogen, the most abundant element in the universe. The duration of a star's main sequence lifetime depends primarily on its mass. Massive stars burn through their hydrogen fuel at an accelerated rate, living fast and dying young. Smaller stars, on the other hand, conserve their fuel over billions or even trillions of years. Stars on the main sequence come in a variety of sizes, masses, and temperatures, each with its own unique characteristics. The hottest and most massive stars, known as blue giants, shine with a brilliant blue-white light. Yellow dwarfs, like our Sun, emit a yellowish-white light and boast lifespans measured in billions of years. Red dwarfs, the most common type of star in the Milky Way galaxy, are incredibly long-lived, with lifespans stretching into the trillions of years. For billions of years, stars on the main sequence shine steadily, powered by the nuclear fusion of hydrogen into helium in their cores. However, even the vast reserves of hydrogen within a star are finite, and eventually, this fuel source begins to dwindle. As hydrogen is consumed, the star's core gradually becomes dominated by helium, disrupting the delicate balance that defines the main sequence. The core begins to contract under its own gravity, heating up and causing the star's outer layers to expand. This expansion marks the transition to the red giant or supergiant phase, depending on the star's initial mass. For stars like our Sun, the hydrogen depletion crisis triggers the red giant phase. As the core contracts and heats up, the outer layers expand dramatically, growing hundreds of times larger than the original star. The contracting core ignites a new round of nuclear fusion, this time fusing helium into carbon and oxygen. This helium-burning phase, though powerful, is significantly shorter than the hydrogen-burning main sequence phase. The star's outer layers pulsate and expand, often shedding material into space in the form of stellar winds. For stars more massive than about 8 times the mass of the Sun, the post-main sequence evolution takes a more dramatic turn. These stellar giants evolve into supergiants, even larger and more luminous stars. Their cores become cosmic furnaces, capable of fusing heavier and heavier elements. Supergiants race through their nuclear fuel, creating elements all the way up to iron in their cores. The core collapses catastrophically, triggering a supernova explosion, one of the most energetic events in the universe. For stars like our Sun, the red giant phase marks a turning point towards a quieter, more gradual end. The core, now a dense ball of carbon and oxygen, begins its final collapse. The outer layers of the red giant are gradually expelled into space, forming a beautiful, expanding shell of gas known as a planetary nebula. What remains is the exposed core, a white-hot ember of the once mighty star known as a white dwarf. As a red giant sheds its outer layers, it creates a breathtaking cosmic spectacle known as a planetary nebula. These glowing shells of gas, illuminated by the intense radiation from the exposed white dwarf, are among the most beautiful structures in the universe. Planetary nebulae have nothing to do with planets. The term is a misnomer, coined by early astronomers who noted their resemblance to faint, fuzzy planets. The shapes and structures of planetary nebulae are incredibly diverse. These shapes are sculpted by the star's rotation, magnetic fields, and companion stars. The colors of planetary nebulae are equally captivating, a testament to the different elements present. While stars like our Sun end their lives relatively peacefully, massive stars, those with masses greater than about 8 times the mass of the Sun, meet a far more dramatic and violent end. These stellar giants, having exhausted their nuclear fuel and fused elements all the way up to iron in their cores, face a catastrophic fate. Iron is the most stable element in the universe, and its fusion, rather than releasing energy, actually consumes it. This creates a dire situation in the core of a massive star. With no more energy being produced by fusion, the outward pressure that once supported the star against gravity disappears. The core, no longer able to withstand its own immense weight, collapses in on itself in a fraction of a second. This collapse triggers a shockwave that propagates outward through the star, ripping it apart in a cataclysmic explosion known as a supernova. Supernovae are among the most energetic events in the universe, briefly outshining entire galaxies. The energy released in a supernova explosion is staggering, equivalent to the total energy output of the Sun over its entire 10 billion-year lifespan. The aftermath of a supernova explosion depends on the mass of the collapsing stellar core. For cores between 1.4 and 3 times the Sun's mass, neutron degeneracy pressure halts the collapse, forming a neutron star. Neutron stars are incredibly dense, packing a mass greater than the Sun into a sphere about 20 kilometers across. Some neutron stars, known as pulsars, emit beams of radiation from their magnetic poles. For cores exceeding 3 times the Sun's mass, the collapse forms a black hole, where gravity is so strong that not even light can escape. The death of a star, while marking the end of its individual journey, is not the end of its story. In death, stars give back to the cosmos, enriching the interstellar medium with the elements they forged during their lifetimes. These stellar ashes, scattered across vast distances by stellar winds, planetary nebulae and supernova explosions, become the building blocks for the next generation of stars, planets, and even life itself. Throughout their lives, stars act as cosmic alchemists, fusing lighter elements into heavier ones in their cores. Stars like our Sun spend billions of years converting hydrogen into helium, releasing energy in the process. More massive stars, in their final stages of evolution, fuse progressively heavier elements, creating carbon, oxygen, nitrogen, and all the elements essential for life as we know it. When these stars die, they expel these newly formed elements into space, enriching the interstellar medium with the ingredients for future generations of stars and planetary systems. These stellar ashes, scattered far and wide, become part of the cosmic cycle of star birth, life, and death. Seeding the cosmos. The interstellar medium as a stellar nursery. The space between stars, often perceived as empty and void, is actually teeming with diffuse clouds of gas and dust, known as the interstellar medium. This cosmic fog, though incredibly thin, plays a crucial role in the cycle of stellar birth and death. It is within these interstellar clouds that new stars are born, drawing material from the remnants of their predecessors. The interstellar medium is not uniform, but rather a patchwork of regions with varying densities, temperatures, and compositions. These variations are influenced by the energy input from stars, both during their lives and in their deaths. Supernova explosions in particular inject vast amounts of energy and heavy elements into the interstellar medium, creating shock waves that can trigger the collapse of nearby clouds, initiating new episodes of star formation. The heavy elements dispersed by dying stars, such as carbon, oxygen, silicon, and iron, become incorporated into these newly forming stars and their surrounding protoplanetary disks. These elements are essential for the formation of planets, providing the raw materials for rocky worlds, gas giants, and icy bodies. From supernovae to solar systems, the intricate connection between stellar death and rebirth highlights the interconnectedness of the cosmos. Every atom in our bodies, every grain of sand on the beach, and every drop of water in the ocean was once part of a star that lived and died billions of years ago. We are, in a very real sense, made of stardust. The heavy elements forged in the hearts of stars, scattered across the cosmos by supernovae and stellar winds, become incorporated into new generations of stars and their planetary systems. These elements provide the building blocks for planets, moons, and even life itself. Our own solar system, including the Earth we inhabit, is a testament to this cosmic cycle. The iron in our blood, the calcium in our bones, and the oxygen we breathe were all created in the cores of stars that lived and died long ago. Their deaths, though marking the end of their individual journeys, paved the way for our existence. The story of stellar recycling is a reminder that the universe is not a static and unchanging place, but rather a dynamic and evolving system, where death and rebirth are intertwined in an intricate cosmic dance. Stars, the architects of our cosmos. As we conclude our journey through the life and death of stars, we come to a profound realization. These celestial objects are far more than distant points of light in the night sky. They are the architects of our cosmos, the engines that drive the creation of everything we know and cherish, from the lightest elements like hydrogen and helium to the heavy elements that make up our planet and our very bodies. All were forged in the fiery hearts of stars. The atoms that constitute our bodies were once part of these distant suns, scattered across the cosmos by stellar winds, planetary nebulae, and the cataclysmic explosions of supernovae. We are, in a very real sense, children of the stars. Stars, through their life and death, shape the universe around them. They illuminate the cosmos, heat and energize planets, and provide the raw materials for new generations of stars, planets, and even life itself. Their influence is felt across vast distances and cosmic timescales, connecting us to events that transpired billions of years ago. The cosmic cycle of life and death. Stars are born, live, and die, enriching the cosmos with their elements. They forge heavier elements and return them to the universe upon their deaths. The death of a star marks a new beginning, forming new stars and planets, Subscribe to Etisla as we witness this cosmic cycle in action.